This interview is with Daniel Cox, Distinguished Emeritus Professor of Physics and Astronomy. After 10 years in the Ohio State University Physics Department, he came to Davis in 1997 and retired in 2022. Dan taught courses at all levels, notably 3 of the Honors Undergraduate Physics 9H series, the course on energy and the environment, and graduate courses on statistical mechanics and biophysics. He also taught in 2 interdisciplinary programs, the Nature and Culture program and the Nanoparticles in the Energy, Agriculture, and Technology program. His research at Davis focused initially on theory of unusual quantum states associated with magnetic impurities in metals, and evolved to theoretical biological physics of DNA, metalloproteins, protein aggregation in neurodegenerative diseases, and computational neuroscience. Dan's career led to Sloan and Guggenheim fellowships and being named an American Physical Society Fellow. His service was largely focused outside the university, where he was elected chair of the Division of Biological Physics of the American Physical Society, and for 12 years co-directed the Science Network for the Institute of Complex Adaptive Matter. That network linked over 60 universities and labs worldwide for workshops and exchange grants, enhancing knowledge of emergent phenomenon in hard, soft, and living matter. He is interviewed by his longtime friend and colleague, Gergely Zermani, Professor Emeritus of Physics and Astronomy.
This is a very special day for me that you chose me to interview you. Over the decades, I always admired your energy, your memory, your skills, and your zest for physics. It's a great pleasure to welcome you to this interview, Dan.
Thank you.
Tell us how it all started.
It was a dark and stormy night. No, I'm just kidding. Well, I was born in Denver, Colorado. I was the youngest of 7 children, and I got interested in science because my father was a chemical engineering major who had to back out because of all those kids, and dropped out about 2.5 years, but was still very interested in science. And then I had 2 older brothers who were really science-oriented, and even one older brother who wound up becoming a computer programmer later on, the other older brother. But I can remember just being fascinated by what my brothers were doing. My brother Dennis wound up becoming a statistics professor at Rice University, and he was really interested in math. And he had when I was in 2nd grade, I remember looking on his nightstand, and he had a notebook there, and this notebook seemed to be to me titled VATB. And at the dinner table, I said, Dennis, what is VATB? And Dennis said, what? VATB? What? And then it suddenly dawned on him, oh, that was the square root of a plus bi. Oh yeah, the square root looked like a v, and the plus looked like a t. He solved the puzzle in real time. But it was like I was exposed to that. And my brother Dave wound up being a very successful petroleum engineer, and he was interested in everything. He looked at Planck's law for radiation when he was in high school, and he was just interested in all the sciences. So I got attracted to it at a pretty early age. And I knew I would be some kind of a scientist. I dabbled in a little bit of physics in elementary school, making a little quiz box for my 5th grade class, where when you took wires and you touched the correct 2 pins together, it lit up the light. And I remember I tried and failed to make a heat engine experiment in 8th grade, but it still was cool. I really enjoyed it. But I wasn't sure. It could be chemistry, it could be anthropology, like you mentioned. I wasn't sure. I just knew it would be some kind of science. And then I moved to Seattle in high school, and I came back from Seattle to Colorado in the between my junior and senior year of high school. And there was a science program at Colorado College, and I was there for the biochemistry, but everybody in the science program had to take a class on Einstein's theory of relativity. And it blew me away. It was just like, this stuff is weird and beautiful, and if this is what physics is, sign me up. This is what I want to do. And so I was decided at that point, going to be a physics major. And then I wound up going to the University of Washington, and my first honors physics class at the University of Washington was so cool, I just said, if this is what it's like being a physics professor, sign me up. I want to be a physics professor. And I can remember like learning Fourier analysis my first year, decomposition of waves into harmonics with a mathematical approach. And I like being so amazed by it. I wanted to like write on the chalkboard on my dormitory floor the Fourier analysis of different series. And I wound up, I think, like boring some people while I did it, but it was fun. And I did indeed was fortunate enough to follow through and eventually become a physics professor. That part was kind of set in stone in college. And I guess a couple other things about college. I spent one summer working in a laboratory at Yale University where my task was to automate a specific heat measuring system and also to build a sample holder for low temperature measurements of specific heat capacity, meaning how the system responds when you throw in a heat pulse, how much the temperature changes when you throw in a heat pulse. And I did fine. I liked working in the lab, but I realized that I was much more drawn to thinking about the material than I was to actually doing the experiments. And so that was when I made the decision, I really want to become a theoretical physicist. But I do like looking at experiments that you can hold in the palm of your hand and thinking about experiments of things you could actually think about, looking at rather than needing a giant accelerator or needing to look out into the cosmos. And so I was really committed to becoming a condensed matter theorist, solid state theorist at that point. And I was lucky enough to get into one of the best places for doing that, Cornell University, for my PhD program. And that's exactly what I did there. And I worked with Professor John Wilkins, who helped set me on the course of my career, and was able to spend my first summer working with him in Denmark, which was quite exciting, my first trip to Europe. And so that's kind of how it all began.
I think that Professor Wilkins had the reputation of being an unusually caring mentor. He really paid attention to his students. How did he help you along the way?
Yeah, John could be tough, but he was indeed caring. He tried to make sure that all of his students got placed, and he kept up with them up until they really got a permanent position in science. And so John was very essential in helping me land my first postdoctoral position. I interviewed at several places, but it was actually a connection with Lou Sham, who'd come on sabbatical to Cornell. And I got to know Lou, and we got to be pretty friendly when he was on sabbatical. And I applied to UC San Diego, and I got a position with Lou at UC San Diego. Unfortunately, Lou and I never wrote a paper together because shortly after I came to San Diego, Lou became dean, and so he just didn't have time. But I was able to continue my interest in work on rare earth and actinide materials that had unusual properties at low temperatures, so-called heavy electron materials, where the electrons moved along so sluggishly in those materials it almost seemed like they were as heavy as a proton, which is like 2,000 times heavier. And it turned out that Brian Maple's experimental group at UC San Diego was just a real treasure for me, that I could interact with Brian and his group. I really enjoyed that. But John then helped me also get a permanent position. I was able to interview at a number of places. In fact, the first offer I got was at UC Davis in 1985. And I actually was interested in Davis, but I was a little nervous at the time as a young scientist because I thought, well, this is an up-and-coming place, but at the moment, it's a very small department. And so when the opportunity came to go to Ohio State, which was a well-established physics department at that point, I decided to take that up. And I started my career at Ohio State. And in my whole time at Ohio State, I continued to work on elaborating these properties of these so-called heavy electron materials. I did, as you did in your career, when high-temperature superconductivity hit. That was a very exciting development, and I worked on that. In fact, I was lucky enough to be at the first big conference where they talked about high temperature superconductivity, which was in India. On the plane over to India, we were all saying, whoa, 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 look at these high temperature superconductors. That's so cool. And we got there, and the Nobel laureate Phil Anderson gave a famous talk outlaying his theory of the resonating valence bond model.
You were at that conference?
I was at that conference.
I didn't know that.
I flew back from India and I immediately told all my colleagues at Ohio State, and they started scrambling to make the materials and started working on theories.
Nice.
And it was just like the most exciting time, you know, just a wonderful, wonderful, exciting time to be alive and be in physics, you know. And I think you and I both were at the famous Woodstock in physics in 1987, where there was an all-night session of scientists just gleefully expressing their results on high-temperature superconductivity. No limits. Everybody could get up and talk, and it was like the coolest thing. It was in New York City, perfect place for public relations. It was just the coolest thing in science at the time.
To tell a bit more about this Woodstock, I remember that it went most of the night.
Oh, it went most of the night. Yeah. I mean, I think I conked out at 1 or 2 a.m., but it was still going on at that point. I made sure to stay for the presentation by my friends from Ohio State, but it was kicked off by the future Nobel laureates, Bednorz and Mueller, and I believe Paul Chu, who discovered the famous higher temperature compounds, somewhat higher temperature compounds in Bednorz and Mueller. That the comment was that what was so cool about high temperature superconductivity was, before that, you had the cool superconductors, which conduct electricity perfectly at low temperatures. You had to cool them down below liquid helium temperature, which is really, really cold, and liquid helium is really, really expensive and really, really rare, because helium floats away as soon as you get it into the atmosphere. It's so light. Whereas these high temperature superconductors, once Paul Chu came along at least, you could only have to cool them down to liquid nitrogen temperature. And liquid nitrogen, as they said at the time, is cheaper than beer. I think that's still true. So there was no problem cooling things down to liquid nitrogen temperature. And so all of a sudden, and everything was reproducible. So all of a sudden, everybody in the world could make high temperature superconductors and do measurements on them. It was just such an amazing time. I can even remember one colleague from Case Western came down to give a talk, and his liquid nitrogen dewar broke right before the famous APS March meeting, and he said, "What am I going to do?" So he built a dewar out of duct tape, and that was good enough for liquid nitrogen, and he got his measurements done and was able to make his presentation at the March meeting. But the Woodstock of science, it was just, you just felt like you were in this kind of golden time of discovery. And as an assistant professor, it was like, oh my goodness, how could this be cooler? You know, this is just so great. And it didn't turn out to have quite, because the materials are complicated, it turned out to have quite the applications promise that we'd hoped for. It still has found niche applications in, for example, processing of signals from cell phones, but not so much as we hoped for in magnets, because the materials are too brittle. But it's still nobody's. The fascinating thing is, almost 40 years later, or actually, 40 years later, we still don't really know for sure what the mechanism is for high temperature superconductivity. So that makes it still an exciting scientific problem.
I think that was really a formative experience for our entire generation.
Yes.
That our field is very much worth studying. This is really amazing things happen there.
Yeah, absolutely. Yeah, and just all kinds of weird fundamental science also that came out of the high temperature superconductors, some of which they behave not like ordinary metals. They call them strange metals. I don't need to go into the details, but it turns out that also in those heavy electron materials, that strange metal behavior shows up. And so I sort of migrated back to the heavy electron materials after my foray into high temperature superconductivity.
So given the degrees which you achieved, that makes you Dr. Strange.
Dr. Strange, that's right. That's right.
But so I believe that many of us got on this field, but then we carved our own way. And I think one of your most impactful work was that you developed and proposed a unique potential explanation for these high temperature superconductors. Tell us a bit more about that.
Well, I don't think it explained the high temperature superconductors, but it took me back to looking at these heavy electron materials. And the thing that I worked on for the first half of my career, in general, was connected to something called the Kondo effect. And that has nothing to do with real estate. It has to do with a Japanese physicist named Yun Kondo, who discovered something quite amazing, which was, well, he didn't discover the experimental detail. He explained something quite amazing, which was that at low temperatures in certain materials, they found that the electrical resistivity, instead of going down, 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 down with temperature, which was the usual trend for these metals, it actually started to go up. And nobody could figure that out until Yun Kondo in the 1960s proposed an explanation, which was that if you had the right kind of little magnetic moments, atomic magnetic moments inside the material, those magnetic moments, if they tended to align the magnetic moments of conduction electrons, each conduction electron is like a little moment in each atom, and these impurity concentrations in the material is like a little magnet. When those little magnets lined up opposite to each other, then you would actually wind up with a increasing resistivity at low temperatures, and that was called the Kondo effect after he explained it. This is a completely esoteric note, but it turned out that what he discovered with the Kondo effect was actually exactly the same phenomenon in a different context, and slightly simpler than what David Politzer, Frank Wilczek, and David Gross discovered in quantum chromodynamics, the study of nuclear, the particles that make up nuclear particles, called quarks and gluons. And it was discovered that quarks actually have something called asymptotic freedom. It turns out, I won't go into any more details because that's jargony, but it just turns out amazingly, like this little thing about a magnetic impurity in a metal actually has very similar physics to these quarks that make up the protons and neutrons of the world. Anyway, putting that aside, Kondo was focused on little atoms behaving like magnets, and those could be iron, those could be uranium, those could be rare earth atoms such as cerium. But what nobody had really looked at was the idea that there could be other kinds of effects if the atoms could change shape. And so what I looked at was the idea that if you took, for example, uranium atoms, not only could those uranium atoms behave magnetically, but those uranium atoms could change shape. They could actually change shape in a quantum mechanical way between a pancake shape and a cigar shape. They could flip from pancake to cigar, pancake to cigar. And it turned out that the way that the electrons went around those could give the same kind of effect as when you had a magnetic atom and an electron. And so, but what was a little bit different was it turned out that as soon as you made that a shape fluctuation, that it tended to pull the electrons together into a pair. And that was the idea that I had for superconductivity, because if you could pull the electrons into a pair, that's actually what you need to make a superconductor. Because the joke I used to tell is that there are two kinds of particles in the world. There are fermions, which are the curmudgeons of the particle world, because you can only put one fermion into one state, so they hate to be around each other. And there's bosons, which are like the Californians of the particle world. And you can put as many bosons as you want into one state, like California. Okay. So you can turn the electrons into bosons if you can make them into pairs. And then they act like bosons. And that's the key idea behind the theory of superconductivity. So this so-called shape or quadrupolar Kondo effect turned out to put the electrons into pairs. Now, I have to give some credit to you, sir, and to your dissertation advisor, Fred Zawodowski, because even before I came along with this, Fred realized, and you worked on it and some other students worked on it, that if you could have an atom that could jump from one spot to another inside of a metal, that it would give very much a similar kind of effect inside the metal. And that was called a two-level system Kondo effect. Mine was called the quadrupolar or shape Kondo effect, and that was called the two-level system Kondo effect. So I worked on that, and it turned out that that actually could also potentially explain some of this strange metal behavior, at least in these heavy electron materials. And so, and then Steve Kivelson, your former postdoctoral advisor, and Vic Emery, thank you. Steve Kivelson and Vic Emery worked on a variation of that could potentially explain the high temperature superconductors, although I don't know if they stayed with that theory over time, but they did do some important work on that. So by going back to those heavy electron materials, I actually was able to have probably my most creative period overall in science, and wrote some papers which still to this day are among my most heavily cited papers, and I'm very proud of, and that really helped to, sort of cement my early career.
And I believe that you then went on and wrote maybe a review paper and eventually a book which really beautifully summarized this field, and it gave it a standing and a coherence.
Yeah, thank you. I wrote a review paper with your former advisor, Fred Zawodowski, and it was a labor of love, but it was definitely a labor. It was written in little brief bursts over about a 6-year period, and we combined our expertise on these unusual Kondo effects, and the publisher liked it so much that they said, we're going to turn it into a book too. And so it's called Exotic Kondo Effects in Metals. I'm proud that I wrote a book. It's not high on the Amazon bestseller list. I never had a book tour, but I'm proud of it. It's a good book. I'm very excited to have
and I believe that its citations are probably around or maybe above 1,000 or
not
something.
yet, but it's getting up
very
there.
it's close. Yeah.
Thank you. Yeah.
So that shows genuine impact, and it's always very good for an initial idea then to really develop into a community and coherence when somebody writes a review, or even more importantly, a book.
Yeah.
So these were your early research years. Then at this time you were still at Ohio.
I was at Ohio State.
At least it started at Ohio State.
I was at Ohio State.
So let's turn the wheel of time forward towards the mid-90s when you joined the UC Davis family.
Right. So I actually very much enjoyed my time in Ohio. Columbus is a lovely city, and it was a great place to start my career. But I'm a Western boy, and I was looking always with the thoughts, well, if I could go back west, I'd really like it, but I want to make sure I go back to a good place, right? And by the time that I considered coming back west again, and there were a couple of positions available at UC Davis, you and Richard Skalatar and Rajiv Singh, and then all of the condensed matter experimentalists had really put Davis on the map, and Davis was a very different place 10 years later from when I applied there to when I first applied at UC Davis in 1985. And so it was like, man, I could take a look at UC Davis again. And so I called you up when I saw that there was a position, and you encouraged me to apply. And I did apply, and thankfully I got the job. And I was very excited to come to Davis and open a different chapter in my career. And I have to say, there were many things about Davis, not only the quality of the physics department, but there were many things about Davis that impressed me. One of them that impressed me greatly was that Davis had a long culture of interdisciplinary research. And at that point, I was very much interested in broadening my horizons. Maybe I had my midlife crisis a little bit earlier than you, but I was very interested in broadening my horizons from what I'd been successful in solid state physics, working on the Kondo effect, to working on something else. And at that time, I began to look around. Once I got tenure at Ohio State, I started looking around and thinking, there are other things going on in the world. And I got very concerned about the environment. I actually taught a class at Ohio State on energy and the environment from a physics perspective. And I'll come back to that because I was able to teach that class here at Davis, too, thanks to
many years.
Right, thanks to Paul Craig and John Jungerman, who had established the class in the physics department. I took it over and taught it for 20-plus years at Davis. Was very happy to do that. And I'd only taught it once at Ohio State. But I was really concerned. I thought, well, maybe I can take and apply my toolkit of physics to problems in the environment, much like you thought. And I began to look, and I had one idea that actually turned out to be right, but I couldn't figure out how to do it right at the time, which was that due to climate change, there were going to be increased amounts of clear air turbulence events in airplanes. And I was able to, with a suggestion from a colleague at Brown, I was able to make an initial correlation between the amount of kinetic energy in the atmosphere and the and the number of clear air turbulence events in the United States. But when I tried to break it down a little bit more specifically geographically, the correlation fell apart, and I couldn't make it happen. Well, 20 years later, people did simulations with climate change models, and they confirmed exactly what I suspected at the time. But I couldn't prove it. And then there were other ideas, like maybe I could work on metal pollution in the environment. Maybe I could work on thermoelectric refrigerators, but I just couldn't see any big advantage. So I had to put that aside, and I kept working on my heavy fermion physics for a few years, but then concomitant with getting involved in the Institute for Complex Adaptive Matter with Rajiv Singh, our colleague, I began to look at problems in biology. And that turned out to be something I could actually do something interesting in and enjoy the latter half of my career working on problems in biology.
To tell us more about it, because I think one of the real benefit of interviews like this is really to demonstrate examples of bold choices to whoever is watching this, because it's really not easy to make such large scale changes in a career. It's scary, it's risky, it's not obvious. So tell us more, how did you change it, and how was it possible for you to really make it successful?
Well, so I mentioned the interdisciplinary climate at Davis. That was already a huge help. And so I right away, once I got here, started talking to people in the honors program, which exposed me to a lot of different people across campus. I had heard about something called the Nature and Culture program, which I taught in for a few years, and that involved trying to bring together science and culture in the form of literature and arts, and have people team teach courses in science and the arts. The degree program existed for a few years, but the funding dried up, and so it didn't wind up surviving. But I really enjoyed that program as well, and that also exposed me to people I had admired from afar but hadn't met, like Eldridge Moores in geology, for example, and people in biology as well. So, and then in addition, as I mentioned, this Institute for Complex Adaptive Matter gave me the chance to take the toolkit that I knew for working on these strange metal problems in physics and connect it to what chemists and biologists were doing with metal ions in proteins and in the environment. And that was where I first began to think, well, maybe there's something interesting with charge transfer physics. And I began to work on that with Rajiv, and we worked on problems involving electron and charge transfer in DNA, which the chemist Jackie Barton at Caltech had shown could be important for some damage and repair processes in DNA.
But biological molecules are so much more complex than what we used to do. How did you have the skills and the courage to jump into that?
Yeah, I just, I sort of did it adiabatically. I knew that the charge transfer problem was similar in some ways to what I'd worked on in the strange metals. And I learned enough about it that I could actually, write some papers in that area. We also came to recognize that there were things that wouldn't work because, DNA is a crazy fluctuating molecule, and DNA depends so strongly on the environment. So we had to do simulations which took into account the environmental aspects and the fluctuating aspects of DNA. We learned as we went what else we had to incorporate. And I wrote a number of papers there with graduate students and with Rajiv. And in fact, my most highly cited paper is a mini review that we wrote about DNA. But we came to realize that while there is truth that there are some processes that the electronic motion can play a role in DNA, it's a fairly limited set. And there was optimism early on that, wow, DNA could not only be perhaps the scaffolding for nanotechnology, because Ned Seaman at NYU had shown that you could by using the sequences of DNA, you could design this remarkable geometric structures that self-assemble from DNA. And then it was hoped that if you could make DNA sort of conduct electricity, oh man, you could turn it into the scaffolds plus the nanowires for nanoelectronics. But DNA is just a really crummy conductor. So there were applications in the sort of understanding how there's gene damage and repair from electronic transfer, but we wound up thinking, well, there's probably not going to go very far, at least from the physics perspective. There might be more interest on the biology side. We're not going to go too far from the physics perspective. And I began to look around for other problems, and that just brought in the toolkits that Rajiv and I had from statistical mechanics, and in particular, we just got interested, the group of us, with postdocs and students, got interested in mad cow disease, which had always fascinated me. Like when I heard about mad cow disease, how do you have a disease that's infectious that doesn't involve viruses or bacteria, and it involves just proteins? And so intellectually, it always fascinated me. And then we realized after we studied one paper that we could actually do a model of that paper, and that launched our efforts on looking at the way that proteins clump together in diseases like mad cow disease and Alzheimer's disease and Parkinson's disease. And that wound up being a large part of my career for the next 20-some years. So we just realized that the kinds of statistical mechanics work that we had done, routinely in our careers and in teaching also could be applied to these problems. And we were able to carry that out, find some interesting things that nobody else had noticed involving possible model for the way that the prions clump together in these proteins clump together in the surface of cells, and also how metal ions can affect that clumping. So we were able to do that work, and then we also did some work on Alzheimer's disease, which involved how the small proteins that stick together in Alzheimer's disease can embed into biological membranes. And I began to sense that, we say that biology is complicated, and it is. It's totally complicated. In fact, it's humbling, because what I discovered very quickly is you might think you have this great sort of reductionist idea, simple idea from a physics perspective. That's going to explain that phenomenon in biology. And there's so many ways that biology will make you realize that it can go wrong. So it's very humbling to work in biology. But it was also like so cool, because it was about things that really were like life and death matters. When I used to joke, like, well, if I talked to somebody on the plane about the quadrupolar condo effect, they'd be looking at me like, really? That's what you work on? And if I talk to them about mad cow disease or about mutations in DNA, they're going, oh, wow, and they get interested in that.
Mm-hmm. I have a question. Why are you talking to strangers in our place?
Anyway, so that kind of, that was all also concomitant with me getting involved with this institute. I can say more about the Institute for Complex Adaptive Matter, but the Institute of Complex Adaptive Matter gave me sort of this, by participating in that, it gave me access to this incredible interdisciplinary framework across many institutions that allowed me to learn and further.
I really want to do justice to that. I watched you, we are office neighbors, and I watched you over decades. You put a lot of energy into it. Yeah. You found a lot of resources. You funded many conferences and fellowships and whatnot. Yeah. Some of them I was beneficiary of. Tell us a bit more. How did this ICAM start? Yeah. What was your vision? Yeah. How were you able to develop it?
Yeah, so I got into ICAM on the ground floor, so to speak. So in the late 90s, David Pines, who was a retired professor from the University of Illinois and was a staff scientist at Los Alamos, got together with Zach Fisk. And I should tell you that both David and Zach were here at Davis in the physics department for a time. So they got together with Zach Fisk because the study of high-temperature superconductivity in strange metals at Los Alamos National Laboratories had started to sort of peter out a little bit. And they were looking for other directions for science at the laboratories. And they pitched the idea of this Institute for the Complex Adaptive Matter both to Los Alamos and to the University of California, which managed the laboratory then. And there was a founding meeting at Santa Fe, and the idea was everybody put in one view graph slide. We didn't have PowerPoint then. One view graph slide with an idea of what complex adaptive matter should be. And out of that, we'll fund some workshops. And I put in a slide which was about this idea of connecting, the strange properties of metals in the environment to metals in proteins and to metals, metal ions in proteins and metal ions in the environment for these strange metals that I had studied. And I wound up connecting with 3 or 4 other people at the meeting, and we proposed the first workshop for ICAM, which was run a year later. That was in 1998. 1999. And this was an incredible meeting. It had people from all over the country. I got to meet some really cool people who hadn't met before, like Peter Wallenus from Illinois and Jose Unishek from San Diego, and Bob Austin from Princeton. I got to meet a whole bunch of really cool people that I hadn't known before. Anyway, so I ran this workshop with Rajiv and with an environmental chemist and a biochemist from Los Alamos, and we ran it at Los Alamos, and it was very successful in bringing people together to try to cross-fertilize these ideas.
Give us some numbers. I think that this is just really remarkable how many conferences.
ICAM is still alive. I'm no longer involved with ICAM. I haven't been for 10 years. But ICAM was started then, and 5 years later, we got an NSF grant, which I wrote the main proposal for and was the PI for 10 years. A big NSF grant from what was called the International Materials Program. We went from, I think it was 6 founding campuses, including Los Alamos National Labs, to, at its peak, about 65 campuses and laboratories around the world in this network.
This is very important. It's really impressive.
And we funded, oh gosh, probably over time, at least while I was involved, we funded at least probably 100 or 150 workshops, and we funded exchange for students to go between laboratories of the order of, there were literally each year thousands of people involved in ICAM workshops and activities. And we ran it at first out of the university president's office, but then we moved it to Davis in 2006 we moved it to Davis, and I was the co-PI on the award for those 10 years, and David Pines and I were co-directors of the Institute for Complex and Adaptive Matter. And when David retired from Los Alamos, he came here for a period of 5 or 6 years as a part-time distinguished professor of physics. David is a National Academies member and had the most collaborations with Nobel laureates of anybody in history. So David's a pretty remarkable personality himself. And then when I stepped away from ICAM, Rajiv Singh took it over, the co-directorship of ICAM. But it's still going. It's still a going concern. It's not quite as big as at its peak because that particular program at NSF was closed down. But
this is, I just want to underline it, that this is just shows how multifaceted your contributions are to our field. So both as a researcher, but also as a facilitator who brings people together and really bringing people from different fields.
Yes.
Just cross-fertilizes, or whatever is the good word, that people learn new techniques, get new ideas, and it really amplifies the growth in each field.
And we also, I'm very proud of that we started a lot of really impressive young people on their careers. And I could just mention, for example, Ivan Smolyuk from the University of Colorado, who got involved in ICAM at Kent State University through, he was in the Liquid Crystal Studies program at Kent State University as a graduate student. Ivan recognized the potential benefits of ICAM, joined up to do ICAM activities right away, and then he became a very successful professor at Colorado and won one of the Presidential Early Career Awards, where he got to go meet President Obama in the Oval Office and shake his hand. Yeah, right.
That's nice.
So we very proud of all the young scientists who we fostered over the years. It's really, I have to say, I'm very proud of my time in ICAM. Very proud of
I admired you from a distance of about 6 feet between our two desks. So we followed most of your research careers. What else do you want to add to characterize the remaining part of your research career?
There were a couple other things. There are a couple other things I would like to add. One is, because of my interest in biological physics, I was able to become the chair of the Division of Biological Physics at the American Physical Society. So there's a sort of 3-year succession you go through until you become chair, and then even the year after you have some responsibilities. And that was, the Division of Biological Physics is the largest division in the APS, the American Physical Society, but it was a really great experience. And also, because of my earlier work, I was named a fellow of the APS somewhere in the 2000s, I forget when exactly, for my work on exotic Kondo effects in strange metals. And then in terms of the research, in addition to the research on the DNA and the charge transfer properties and metalloproteins and so on, and also the work on protein aggregation, there are, I guess, maybe two more things I'd like to mention. One is that a number of us recognize that the work on protein aggregation, you could actually sort of take the evil of that, because protein aggregation diseases like Alzheimer's and Parkinson's, where the proteins clump together in ways the body's not able to process, those obviously are not good. I mean, Alzheimer's killed my best friend last year, and he also had Lewy body dementia at the same time, which is a different protein that aggregates, the same protein that aggregates in Parkinson's disease. So, these diseases are terrible diseases, but we recognize that if you took the way that the so-called amyloid principle that those diseases aggregate by, you could design protein arrays that could be used for things. We hatched the possible idea of using them for photovoltaics, so that was maybe sort of growing photovoltaics, but that was sort of a dream that never was realized. But we were able to secure some funding from the university to go after this idea. And it was an interdisciplinary group of chemists, physicists, engineers. And what I will say is that we gave a really good try at a startup company out of that, where we wanted to be able to use our alternate proteins to substitute for antibodies in disease detection and treatment. And we got really close during the pandemic. But unfortunately, we were just 6 months to a year behind, and when the pandemic ended, there was no longer any investment in viral diseases from venture capital, and so we gave a couple other things a try, but we realized, we gave it a shot, but we didn't have the right timing.
But this is again something to underline, that I really admired your courage and your initiative, because it's very not obvious for a professor to really lean into it and say, I will give it as they say, a good old college try and push it as far as I can. So that was another impressive chapter in your life.
Well, thank you. And the other thing that I worked on was I got interested in neuroscience from a distance because of the brain initiative that President Obama started. And in my sort of closing chapter as chair of the biological physics division, I did a tutorial workshop on the brain initiative, organized that and ran it at the American Physical Society March meeting. And it turned out there were a large number of students in the department who wanted to work on theoretical neuroscience. And there was nobody else to do it. So I sort of said, well, I'm not really equipped to do it in the sense that I don't have a great depth of knowledge, but I'll see what I can do. And there were about 5 or 6 students, and I wound up working with 4 of them. 2 of them wound up working with other advisors and graduated and got either a postdoc or like a really good job working on AI. And then the other 4 have graduated with me, and one is working in high tech in China, and one as a postdoc at Dartmouth, and one is my last graduate student. He's about to finish. But that would turn out to be a very exciting thing to do also, just because maybe like with astrophysics, neuroscience with physics tools is one of the areas where lots and lots of data is rolling in. And I am fundamentally a believer in the idea that physics is a experimental science, that even as a theoretical physicist, I have to rely on the presence of data. I don't believe you can be a complete constructionist in physics. Sorry people who do superstrings. But so what are the 2 areas that I felt as I looked at towards the end of my career where that lots of data was rolling in? Cosmology and astrophysics, and experimental neuroscience using physics techniques to do the measurements. So it was very exciting to I won't say that I had any radical breakthroughs or anything, or that my students have. They've done good, they've done well, but it's just exciting to be able to learn about that at the end of my physics career. So,
absolutely. You brought up some of your students and the obvious delight you have mentoring them. Tell us a bit more about the students who came through your research group. What happened to them thereafter?
I'm proud to say that you know, I've kept tabs on most of my students who've graduated, all but a couple I know where they're at. But I've had, I think, 22 PhD students over the years at Ohio State and Davis, mostly at Davis, where I've spent a larger part of my career. I'm happy to say that you know, one of the first students I had working on biological physics, Robert Endres, he wound up being a professor at Imperial College in London, and one of my students from Ohio State, Zhang Han, wound up being a professor of physics at Buffalo University, or SUNY Buffalo as they used to call it. And then one of my third biological physics student, David Mobley, wound up becoming a professor of pharmaceutical chemistry and chemistry at UC Irvine.
Wow, these are really impressive.
Yeah, he's doing very well. I also had a lot of postdocs over the years, and they postdoctoral researchers, and they all did well. Unfortunately, Mark Giroux passed away from cancer, but Mark was my first student, and he did extremely well working on sort of extensions of that condo idea to so-called dynamical mean field theory, and Mark was one of the leaders in that field. And another one, sadly, who passed away was, oh gosh, now I'm forgetting his name. I'll skip over him for a second, but he was a professor at Hebrew University in Jerusalem. And I have a student who became a professor at Dortmund, a student who became a professor at, or postdoctoral researcher who became a professor in Japan, one who worked with both of us who's a professor in Hungary. They've all done quite well.
Approaching 10, the number.
Yeah, and I have 3 who decided they wanted to teach at small colleges, also in this country. 3 students who wanted to teach at small colleges. So they've done well, and a lot of them got industrial positions. One of my students, Jesse Singh, wound up working for Facebook, for Fitbit. Now he's working for Google.
I think really it's one of the source of deepest joys for our career is to be the mentor of young talented people and just launch them and then watch them fly high.
Yeah, exactly. I've definitely enjoyed that. Yeah.
Good. Another aspect of interacting with students is, of course, teaching.
Yes.
Classroom teaching. Yeah. Tell us a bit more. How did you approach it initially? How did you evolve as a classroom teacher? And so?
I evolved, fortunately, in a very positive way. I actually won a teaching award as a graduate student at Cornell, being a TA, and I had some of the most wonderful professors at Cornell. But just as an example of what I mean by evolution, when I first got a chance to teach statistical mechanics, I just did I didn't do a sort of thoughtful analysis. I just did a counting analysis. I said, well, if I look at the amount of hours that my professor Michael Fisher covered in one semester at Cornell, and I look at the number of hours I have to cover the same material for these graduate students at Ohio State, they're the same number of hours. However, mine were compressed in 10 weeks and his were 15 weeks. And I didn't take into account, it actually helps to have that time to think about it. So I did it. I took all of the material that I saw Michael Fisher cover, put it in my own terms, and covered it in 10 weeks. And my students looked at me like, are you kidding me? And they were absolutely right. I tried to do way too much in 10 weeks, right? So I learned from that you have to really look at the structure of what you have and work with also every class, even if it's the same material. Every class is a little bit different, and you have to look at the class that you're teaching at the time and the students that you're teaching at the time and work with them.
So which teaching do you enjoy more, the last class to hundreds of students or the smaller group-like settings?
I almost never enjoyed the really big classes. They were okay, but I mean, you and I both share a level of performance. I've done improv, and I actually, when I was a college student, I performed one-man shows as Isaac Newton and Einstein at a science museum in Seattle.
I didn't know
and
that.
I also did a liquid nitrogen demonstration as Groucho Marx with a whole bunch of Groucho-like jokes that I made up for the demonstration. But I did all that.
I see that YouTube.
Yeah, it's not on YouTube, unfortunately. YouTube wasn't around then. But it's maybe on Flintstones, the rock
Yeah,
tube or something. But anyway, so I mean, taking an acting class right now, jumping ahead to what I'm doing in retirement. But I've always loved the performance aspect, and that can come out in a large setting. But I really enjoyed working with smaller classes, and I especially taught a large number of the honors physics for undergraduates. I loved every one of those. And the students, the cool thing about the honors students is, man, those students really loved physics. They were almost all physics majors. They really wanted to do physics. It was their first exposure to college level physics. Oh, it was so much fun. The enthusiasm, the questions, and the material. It's like one of the classes taught statistical mechanics the way I wish I'd learned it. Instead of starting with thermodynamics and starting with these crazy, relations that somehow these French and English scientists and engineers figured out in the early 1800s, you actually started with Boltzmann. And it's like, oh, if you count the atoms, you can actually understand how the second law of thermodynamics really works from the law of large numbers. It's like, holy moly. That's how I taught, that class. And also waves and connecting waves on strings to quantum mechanics. I love those classes. I also loved an undergraduate class I taught on energy and the environment, which we alluded to earlier. And for me, that class was always a chance. It counted as an ethics credit for engineers, but that class was always one where you'd find out, well, I'm taking this because it fits my schedule and it's an ethics credit. By the end of the class, the students would have sort of an appreciation for what environmental problems were, and many of them decided they wanted to work in that area. It was a mix of physics and engineering and environmental studies students in that class. I taught that maybe 20 times over the years.
And I think that in smaller group settings, you can give the sense of importance to every student, and that is really motivating them as well.
Well, and I enjoyed the graduate classes also because those were always at the edge of intellectual, the intellectual frontier. They were closer to the intellectual frontier. So I enjoyed those classes too. Yeah.
So good to hear. Tell us about your relationship to the department, to the campus, to the colleagues.
Yeah, so I agree with you that this is an incredibly collegial department. And I was fortunate to come from a very collegial department at Ohio State where the same philosophy was there. If you want to make a good department, hire people that are smarter and better than you. And we kept doing that at Davis over the years. I have to say, the people who came after me, it's like, man, I don't think they're doing way better than I did. And I don't think I was a slouch. I did mention it, but when I was at Ohio State, I got a Sloan fellowship, an AP Sloan fellowship. I got the Presidential Young Investigator Award, which was kind of the forerunner of the current NSF Career Awards. And then I was also named a lecturer at same lecturer at the University of Lausanne, which was an honor. So I had those honors at Ohio State. So I wasn't a slouch, but it's like, man, these people we're hiring are so good. They're so much better than us. And also the collegiality across the disciplines at Davis. The boundaries, the walls between departments were very low, and the graduate group structure was incredible to appreciate.
Well, but I think that you were probably the professor who took the most advantage of that, of all of us. So many of us tried different things that many ended up staying within the departmental walls. But yeah, I just watched you interacting with so many other departments and really benefiting and creating synergies.
I did. I enjoyed that. And I also just saw, how Davis went from when I came back and took the job in '97, around 20 to 22,000 students, up to 40,000 students. It became just a huge major university on a par with Berkeley and UCLA and UC San Diego and Irvine. And it's just like, wow, Davis is right there, and it was amazing to me to see that growth in Davis. And the town also became, I didn't wind up living in the town, as you know, because I met my late wife in San Francisco and decided that was a better location for me to live in. But the town of Davis became a wonderful, vibrant community, and things that contributed to that were like the Mondavi Center and just lots of great restaurants and things. So that was all, seeing Davis grow up in that way right before my eyes was quite amazing. And it's a great university, Like every university, we have our we have our problems, but it's a great university, and just to see it become one of the, recognized nationally and internationally as a great university is really thrilling, and to be a part of that.
I totally share the feeling, and you were so kind, and in the later stage of our discussion, you asked me about my vision of the future, that where things are going. Let's start with what do you think about the future of our field, the physics?
Yeah, well,
physics research.
as I alluded to, I think that in terms of growth areas in physics, astrophysics and cosmology and sort of neurophysics, I see as two areas for outstanding growth. I don't think the other ones are necessarily going to go away, but I just see those as areas where there's data coming in. It's likely to keep coming in for years and decades, and so there's a chance to really do something there. I have to be candid. I retired in 2022, as you did, which was exactly when ChatGPT hit. And I have to be honest. I think there's going to be some serious disruption of universities because of AI. I'm not sure exactly what's going to happen. It's going to change. It already is changing, but I think it's going to dramatically change the way that we teach. It's going to change research too, because some of the things we know that AI can work sort of like a super Mathematica or super Wolfram Alpha for doing calculations and things. It's going to change what we do, and I'm not quite sure how. It's exciting to watch from the outside.
It's such a mixed feeling, because on the one hand, AI makes so many things possible and accelerates things tremendously. On the other hand, the social implications on entire large groups of the employed classes are really becoming endangered in this, and how will society function? It's non-trivial.
Well, and one of the things that's always fascinating to me as a physicist is sort of the Prometheus problem. Prometheus brought fire, and of course then the gods punished Prometheus for taking fire to the humans. The physicists have repeatedly brought fire, so to speak. The most famous example being the nuclear bomb, and physics has had to live with the fact that we brought that powerful force of destruction into the world. In a way, we are tied to AI too, because the neural networks that are the basis for AI have a strong connection back to the work of John Hopfield and later Geoffrey Hinton, and of course they were awarded the Nobel Prize in Physics just a couple of years ago for their work on neural networks and deep networks for Geoffrey Hinton. So physicists bear a certain responsibility there, and by bringing that particular fire to the world, we're transforming the world in ways that I don't even for sure know how it's going to go. But I do know that, coming back to our mutual interest in the environment, that it takes large amounts of energy and water to run AI in the current format, and AI can kill a lot of jobs, possibly even professors' jobs. At the same time, if we figure out how to use it in a smart way, it could actually enhance the science dramatically, and that's my optimistic take on it. I use it some. I'm not a complete Luddite on it, but I don't know for sure where it's going.
It is interesting how to give advice to the young students who are now seeking their way forward, and it's a little bit disorienting times.
Yeah, absolutely. But it's also, there is the potential for real excitement and creativity, because it's suddenly a tool which, if you figure out how to use it right, can make possible new discoveries that we haven't had before.
One of the early really impressive applications of AI was when those guys predicted the structures of hundreds of thousands of proteins, which
with
people
AlphaFold.
couldn't do it before.
Which also won a Nobel Prize in chemistry the same year that Hopfield won the Nobel Prize in Physics. Yeah, absolutely. AlphaFold I've used, and it's actually it sort of in some ways has solved the so-called protein folding problem. How do proteins go from a random polymer to a useful compact structure? When if you predicted it naively, it would take many universe lifetimes to do that. And AlphaFold has sort of solved that sequence to structure problem to a large degree. It's certainly advanced it dramatically. And I had friends like Jose Unashik and Peter Walnes. That was their career, coming up with protein folding theory, and they've kind of been superseded by AlphaFold.
I see. We are very close to the end. Is there any closing thought you want to share with us about the vision of the future, looking back at your career? Or
I just want to say that I'm very grateful to UC Davis for the majority of my career being spent here. 25 out of 35 years as a professor were spent at UC Davis. It's been a wonderful university. It's been a wonderful place to kind of come to my career midway through and finish my career, and also along the way get married, raise a family, and enjoy this beautiful part of the world that we live in. So I'm very grateful for that. I know I had a bit of a depressing note about AI, but I remain optimistic, and I feel like the universities have been around for, some of them for over 1,000 years, I think, right? Or about that. They've been around for hundreds of years. And we keep reinventing ourselves. And I think the most amazing thing about being a university professor is just that probably no other job gives you the freedom to reinvent yourself, even with the constraints that are being placed on universities these days. I don't think there's any other job that gives you the chance to reinvent yourself the way that you and I have in the course of our career. And what a great gift. And also to be able to share that process with generations of young people, smart young people, and to see them blossom and grow. That's what the university offers, and I think that will continue, even with all the challenges. I think that will continue.
These are beautiful closing thoughts. Dan, it has been an honor and privilege to be your colleague and your friend for the last 30 years.
Same.
Thank you.
Yes.